My name is Lloyd Tinkler. I work here at the University of Sheffield's Advanced Manufacturing Research Centre, where we've been trying to address Grand Challenge 2.3 within the Future Electrical Machines Hub. And this is looking to develop more flexible and customisable processes for electrical machines. And this is kind of address the middle ground between what's appropriate for prototyping and mass production and trying to find something that's more suitable towards higher value but lower volume products. And this fits really nicely with everything else that we do at the AMRC, looking at those kind of advanced manufacturing processes. To that end, we've been developing remote laser cutting as an alternative to conventional laser cutting for electrical steels. And we've also been looking at robotic winding of coils as the basis of a flexible manufacturing cell that can do a number of processes within the same envelope.
My name is Dr. Alexei Winter. I am lead engineer for electrification at the University of Sheffield's Advanced Manufacturing Research Centre. And the cell you can see behind me is the FEMM hub remote laser cutting cell. And the purpose of the cell is to produce electric machine laminations for electric motors. The core of the electric motor, although it might look like it, is not a solid block of material, but is in actual fact a stack of very thin laminations which must be produced from sheet material. Laser cutting is very accurate and reliable, but the heat of the laser can damage the electromagnetic properties of the steel. And so the idea behind this cell is that we are steering the laser very quickly using a galvanometer so that it moves very fast and interacts with the steel for only very short times. And the reduced interaction time between the laser beam and the material means that the heat effect is minimized, the electromagnetic properties are maintained, and overall your machine performance is higher. Here at the back of the cell, this is the control cabinet, and this is the brains of the system and encompasses all of the many systems that are involved in making the whole cell work. The computer controls everything through a network. We have a communications box that talks to the laser system. There are all the drives that control the motion control systems in the cell. There are safety systems, there are measurement systems and power and communications with an extraction system and a chiller as well, which all operate automatically. We've calibrated everything so that the motion control is able to operate with just a few microns of accuracy. In terms of the results, we've had quite an extensive experimental campaign and produced samples that have been tested for their electromagnetic performance. And the headline result is that this laser system demonstrates a significantly better performance in terms of the electromagnetic performance of the steel than a standard laser cutter. The plan for now is that we have a brand new laser. So previously we were using a continuous wave laser which was just on all the time, and the next laser is a nanosecond laser which pulses with pulse durations down to 30 nanoseconds, which seems incredibly fast. The perceived benefit of that is that we will have much more vaporization of the metal and much less melting, and therefore much less heat soaking into the component and much less damage to the electromagnetic properties. So we're hoping that this will demonstrate a further improvement to performance.
My name is Gianmarco Pisanelli. I'm a tech fellow in robotics research here at the AMRC, and I designed this robotic winding cell. The idea behind the project was to sort of create or provide some flexibility and adaptability to the manufacturing process of electrical machine. And that's because at the moment the winding specifically is done via CNC machines. These machines are very fast and they are very accurate. But the problem is they're very specific and they're very expensive. So when it comes to sort of trialing new methodology or new sizes of motors, new shapes or new topologies, these systems are too specific and they need to be redesigned completely from scratch. And this becomes very prohibitive and doesn't really allow for prototyping. So what we've proposed here was using robots instead of these CNC machines to provide, again, some flexibility. What we've done specifically is we created an end effector, a needle winding end effector that you can see there. And that end effector is trying to replicate the needle winding process What we found out during the project is that tension is very crucial for the process. In fact, if you have too much tension, the wire risks to be damaged. You can have damage to the insulation, or you can elongate the wire, causing more losses because of the increased resistance. But also, if you don't have enough tension, the wire does not get deposited properly, and it will just cause what's called a wild winding. So the wire just disperses and it doesn't stay put in place. Finally, this is sort of the first time that we know of that a robot has been used to do winding of electrical machines, and we've published a paper on that. We presented it at the coil winding exhibition in Berlin, and it gained quite a lot of interest.
So in addition to a lot of the exciting results that have come from the remote laser cutting and the robotic coil winding, the FEMM Hub has really acted as the starting point for a lot of industrial collaborations and a lot of new capability at the AMRC. And in the coming years, we're going to continue on that journey and try and put the UK at the forefront of the electric revolution.